All right, it's time. Any questions from the homework writing project? Adam? Adam?
Can you hear me?
Yep, I can.
Could you go over problem 28, homework 3.1?
Dun, dun, dun. $28. Have we done this in class before? Good. Then let me go over all the details. Hx equal this. Okay, you want to find h prime x. That's your job. So from now on, we are familiar with this. Every time you see an absolute value, that basically means you have two options. Now you have two absolute values. That means two options each. You have four options in total. Okay, so that is going to be x minus 1 can be either this or this, and x minus 9 can be either this or this. With that in mind, the two together have four possibilities. This is one. If you feel confused, always put a parenthesis so you won't make mistakes. Okay. All right, we have four possibilities, each one taking two possibilities. Now you need to think about when to take which one. Okay. For the first one to be true, you need to make sure that this is bigger than 1, so you take the positive one, and this is bigger than 9 to take the second one. So together, the first two should require x bigger than 1 and x bigger than 9. Together, this implies x bigger than 9. We'll guarantee both. Okay. The second one, you want to make sure x is bigger than 1 and x is less than 9, so you will take a negative sign here. Therefore, you would take this one when x is bigger than 1, less than 9. For the third one, you need x less than 1 and x bigger than 9 at the same time. From here, you can see this is not possible. You don't have anything which is less than 1 and meanwhile bigger than 9, so you will never have this kind of format. Finally, the last one, you need to require x less than 1 and x less than 9. Together, this is x less than 1. So this third one is not okay. Is the analysis making sense for how to remove the bar of the absolute value? It really depends on where x is. Okay. With that in mind, now you can write down the whole function. You have three possible formulas. The first one is 2x minus 10 coming from this. The second one comes from this. You can do the verification. It's going to be 8. And the third one comes from this. It's going to be negative 2x plus 10. And then this works for x bigger than 9. And this works for x is less than 1. This is x. Sounds good? Okay, this is before we take the derivative. We have three formulas. Then of course, when we take the derivative, we will also have three formulas. 2, 0, negative 2 coming from each of the corresponding function. And then of course, it only works for a limited time. That will be the derivative. Sounds good? Okay, so just a heads up, for piecewise defined function, you of course have piecewise defined derivative because each different function formula have a different derivative. So the only thing that can go wrong is on the ending point, which is where they intersect each other. The good news is usually we don't care too much about that point unless we're specifically required to do so. Okay. In this case, they don't want that. Okay. Other questions from the homework? Okay, let's continue. 3.4, we did something called the chain rule. Okay, it's used to handle the function composition, where you take one function and put it into the input as the other function. Something as good as sine x squared prime. 3 examples now we know. This one has 2 things. You first take x, you go to x squared. You take x squared and go to sine x squared. Here you applied sine, here you applied x squared. They have their corresponding derivatives to be cosine and 2x. So when you take the derivative, you kind of go backwards. You do the cosine first. Don't do anything about x squared. Then you times the derivative for later. And you do one at a time until you hit the last one. Okay. I think we did many examples last time, from easy to hard. We should be okay with this now. The rest you need is just more exercise, and you can do it in your web work. Chain rule is usually the hardest one for this chapter. Make sure you do enough exercise until you feel comfortable about it. Okay, product rule, quotient rule, everything before is, I won't say easy, but as long as you memorize the formula, nothing can go wrong. But for this one, it can be confusing at first. All right, with that in mind, now we're ready. We're ready to do something which is a leftover from last time. The derivative of exponential functions. Okay. If you try to recall, we did this in 3.1. We find this. That is all right. But what we didn't do is exponential function can have other bases other than e. For those kind of things, we never did. Now we're going to handle it by the help of the chain rule. Okay. Let's just take 2 to the x. Let's think about the derivatives. Number 1, it's not going to be this. This only works for e to the x. Okay. So what can we do? Well, you need to think about everything in terms of algebra again. Recall, in pre-calculus, if you have exponential, okay, for example, you have 2 to the 8th, you have the freedom to change the base to be base 4 and then do this. Sounds good? It's able for you to change the bases and you stay the same. The only thing you need to do is just you need to change the exponent. Then you talk about actually everything can be changed in terms of base e. That will be the key. So take this one. Don't want base 2, I want base e. The first thing you do is you take this. From here you can see this is still 2 because e and ln cancel each other. Now what you can do is you can factor things out by taking e, not factor, multiply. This is almost like e to the third, e to the square to the third, which is e to the 6th, right? What you have here is nothing but just not a nice number, but the same rule still works. You have ln2 times x. Good so far? Okay, now can you take the derivative of that? you need to ask yourself, what's that? That is basically E x with a number here. It's a bad number. It's ln2. Sounds good? So the way you do this will be exactly similar as the way you do this. Now let's do the easy one first. How do you handle this? E with a 2x here, that's going to be e to the 2x. Then by the chain rule times this, then I have e to the 2x times a 2. Sounds good? This one then will be exactly the same, except you don't have a nice number as 2. You have a bad number as ln2. But more or less, they're just numbers. So note, this is just a constant. The derivative of this one is 1. Together, it's e to the ln2 times x times ln2. Now you can recover this to be 2 to the x ln2 again. Sounds good? Okay, so this is what we have for any general exponential. Okay. The formula is given by for a bigger than 0. The way to do it is actually take this one, you somehow change it to be e to the ln x, apply the chain rule, and finally got this one. We exploit the fact that e to the x is e to the x. Then we can actually somehow just do this one by doing a small modification. Okay. Sounds good? From now on, any power you can do it. 3 to the x is going to be 3 to the x times ln3. 1/2 to the x is going to be 1/2 to the x times ln1/2. So it's almost the same as itself, but adjusted by a small number. Now, if you think about e to the x, it's basically e to the x times ln e, according to the formula. But what is ln e? That's exactly 1. Okay, so even e to the x itself follows this rule. It's just e is just a special number, such a special number, such that ln e just happened to give you a 1. Okay, but everything else will give you some leftover constant. All right, doable by chain rule. The key is know this formula. That's all. That's all for chain rule. We will move on to solve the last leftover of the derivatives. Before we do that, any questions regarding chain rule? Or do we need more examples on how to do chain rule? If you think we need more example, just raise your hand. No. Click yes. Don't raise your hand. Let's do more. Let's do a long one. Let's create one by ourselves. Let's do 2 to the 2 to the 3 to the cosine x squared prime. Okay, try that. Nick?
Why is it positive sign and not negative sign?
Dun, 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 dun. Dun, dun. Should be negative sign. You're right. Then I put the negative sign in the front. There's only one of them. Hmm? If you're okay with this example, you're more than prepared for the exams. This will be definitely harder than what you will see in the exam. So take some time and ask questions. Jordan?
So do you care on the exam? Do we have to move the negative sign to the very front?
Doesn't matter as long as you keep the bracket.
Okay.
It's just like if you remove the bracket by putting a negative sign there, people may confuse it by minus.
Okay.
Right. So as long as I know it's multiplication, it's fine. Aaron?
For the exam, do you want us to like go through the work of showing like how you
Okay.
did the exponential, or?
You don't have to.
Okay.
Yeah. And for the question like this, actually, if you are later, you become proficient. You don't have to write things in this way. Okay. What you need to do is just take from here. This is usually what I do. Hopefully I'm right. What I'm going to do is I'm going to do it straightforwardly. I break the first chain. And automatically I start to do the derivative of this one without having to write it in this way. Okay, so I can actually do things in this way. Do that. Keep in mind, I was doing this. Then I realized, okay, cosine, fine. And then 2x plus 1/2 x to the negative 1/2. Sounds good. So you don't have to actually break them into 4 steps. And basically what you're trying to do is you're trying to rewrite this part with this part. And the reason I'm doing this in the notes is try to make sure that you understand the structure. Okay. So for me personally, I think all chain rule problem will take only one line. That is, do the first chain and then automatically the second, automatically the third. And then maybe another line just in case you want to combine some terms to simplify them. Should be no more than 2 lines, but each line can be really long. Okay. So feel free to do this if you're super proficient with chain rule already. The bad thing is it's gonna be hard for me to give you partial credits. Okay, if you write everything this way, you may mess things up. Okay, Jordan?
Yeah, I just had another quick question. So when it's like an algebra, I guess. When you combine the natural logs, when you're multiplying, you just multiply the numbers on the inside?
Yep. This comes from a log property. That is ln a plus b. No. ln a plus ln b equals ln a plus b. A times b. Yeah. So what I did was ln2 plus ln3 equals ln2 times 3, which is ln6.
Aren't you multiplying those together? ln2 times ln3?
Actually, no. ln2 plus ln3, you multiply 2 and 3, not ln2 and ln3.
I guess I was saying like in the actual problem, like when we took like 2 to the 3, whatever.
You are right.
ln2.
I was doing the wrong thing. Yeah, you are right.
Okay.
I was wrong. Yeah. Man, I'm gonna lose a lot of points for doing this. Still, yeah, I'm the one who grades. So I would say like the minus sign and the ln wrong thing will cost me 1 point out of 10. So still not too bad. You're right. I should be combining them if I'm doing plus. And there's no way to simplify this other than just write it that way. All right. If you could follow what I have here, you're all set, okay? You just need more exercises from your homework. So go ahead and do it and bring the questions back. Then we can go over more. There's nothing difficult with chain rule from what you see here, other than figuring out the structure of the original function, who composed with who in which order. Actually doing it is pretty easy. It's just seeing the structures. How many different chains do you have? In this case, we have 4 chains, or let's say 4 functions, 3 chains. Okay, and which one to break first? That's probably what you want to focus on, which to break and which to keep. Okay, for example, break the 2 to the x, that chain, but keep the whole thing here. That's basically the core of doing chain rule. One thing at a time. All right. One last thing. Remember, we have a whole thing there. Simple functions, okay, plus, minus, times, dividing, quotient rule, product rule. Finally, we have F circle G, which is the chain rule. The only thing left is how to do log and how to do trig inverse. Okay. Of course, we want to get all of them through one technique. That is, log should come from E, and arctangent should come from tangent, because you guys are inverse function to each other. So what we really want to do is, we want to do the differentiation of inverse function. Okay, that will be what we will cover, which is actually better than this. We can do even better than this. We can do implicit differentiation. Okay, the key is implicit. Explicit, implicit. When we say some function is explicit, basically that means we already have a nice format of y equals fx. For example, y equals x over square root of 1 minus x squared. This is what we call explicit, because you write y as a function of x. Okay. However, in general, we do know another way to represent a function which is not explicit. Instead, we do an equation. For example, a circle. Do you see the difference now? It's an equation. For this case, I can still solve it. It's going to be a pain. But if I make things a little bit more complicated, then you know you should give up. There's no way I can solve y as a function of x, because algebra simply just doesn't work. Still okay? We call those implicit function. Okay. Now what we want to do is, we want to show how to do the differentiations for this type of equations. Okay. Instead of something like this, which is pretty easy, we got all the rules and formulas. To do that, why don't we just start with the easiest one? The unit circle. Okay, find the derivative y prime of x squared plus y squared equals 1 at the point square root of 2, square root of 2. Number 1, we don't have an explicit function. Then, does this question even make sense? Well, let's draw the thing. This is a unit circle. Okay. Do you know where this point is? That's pi over 4 here. Okay, if you wonder, this is exactly 45 degrees. Okay. So what you're trying to say is, here's the circle. Can you find the tangent rate at this point? Does the question make sense? Does this one have a tangent rate? Well, tangent rate is the slope of the tangent line. Can you draw the tangent line? Yes. Okay. What's the tangent rate? It's negative. Moreover, if I'm going to guess the y prime is actually -1. 45 degrees by geometry. Sounds good? So from drawing, at least this question makes sense, which means this is doable. Maybe it's hard to do, but it's doable. Okay, it's not ridiculous to ask this. All right, then how do you do it? Well, there is a way. The first way, that is, even though you're implicit, I can change you to be explicit. That is, I take this, okay, I solve for x, I solve for y. Now we know the positive one is for this, the negative one is for this. Because our point is here, I'm going to take the positive one. Starting from there, chain rule, product rule, quotient rule, whatever, okay? Y prime give you sounds good. Okay. This is certainly doable, but this is not good. Number one, you are trying to avoid the problem. You didn't solve it. You try to avoid it by changing it to something you can solve. Okay. Number two, this is a lot of algebra. It can be very complicated to solve for y from x. You know how hard it is to solve an equation, right? Number three, this may not even be possible. Like the example I gave to you just now for this one, you simply just can't solve it. At least not in an elementary way. Good so far? Okay, so keep in mind, if you see something implicit, this is always an option. And my comment is not a good option, not a good one. But if you're desperate, that's something you can try. Of course, what we want is, we want to just go from here directly and solve it. Now let's see how we do it. You want y prime, right? That is differentiate y with respect to x. Then how about we just differentiate it and see what comes out of it? Just do it. Okay. That's the only way we can create some derivative, right? Now, we have several parts. What is the derivative of 1? A constant. What's the tangent rate of a constant? 0. That is good. On the left, I have the derivative of 2 things plus together. At least I can split them into this. Okay. From here, I can see this one is no problem. That is just 2x. Still okay? So the part you feel confused or you get stuck will always be this part. How are we supposed to handle this? Let's take it out and see how we're supposed to do it. What are you trying to do here? You're trying to do this, okay? What's the trouble? The trouble is this variable and this variable are different. Sounds good? I certainly know this. If they're both x, the answer is dx 2x. If they're both y, the answer is certainly 2y. Still okay? But we have the worst case. That is on the top is y, on the bottom is x. Well, then you need to ask yourself, what is this? At least I can do this for dy. Then I will be able to have 2y. Good. But this is not the whole story because I need dx, so I have to multiply by this. Okay, and that offer me 2y, and what's this? Y prime. That is by differentiation, by doing the ratio. This is what we got. Sounds good? Y squared and x, they were connected by y. So I added y, I deleted y. Okay, that is something served as a bridge between these two. But somehow I end up with this. Good so far? Let me write it down. What you just did is you basically take this one, you took the derivative, and you got this. Okay, does it look like something? Okay. What if you have this? You take 2 sine x, then you times cosine x. Right. Or maybe sine x prime. Still okay? So this is exactly the same process, except in this case, you know y is sine x. In this case, you don't know the formula of y because it's implicit. Still okay? But the rule should still work though. So if you have some function, you do the square, you do the first part, and then you times this. That is actually the chain rule. This y is nothing but your g there. Okay? So two ways. Either you go with the ratio or either you go with chain rule. Nonetheless, you end up with something, just pretend it's a function of y, but when you finish, you times y prime. That's what we call chain rule. Still okay? Settled. With all that, let's redo this one. Okay? Take the derivative on both sides. Zero, 2x, 2y times y prime, according to the chain rule. This is still true. Your question is, what is y prime? Well, it's here. So let's solve it. That's all the work you need to show. Does everything look good here? The key is, whenever you have a y, you want to take the derivative of the x. What you do is you take the derivative with respect to y. That's like regular. Just remember when you finish, it's times the y prime. Okay, that's the only thing you need to be careful of. Nick?
So once you get to this point, would you just plug in the points then, and that's how you'd get -1?
So, still keep in mind that is, I want to find this. The changing rate, then y prime equals negative. Yep, the answer is going to be -1. You can even try more. What do you think the point here, the derivative of the point here, 0, 1? Does it match your expectation? It's horizontal. Okay. Also before, when we do the exams, we say, hey, the changing rate here is vertical up, right? So what you have here should be an infinite changing rate, or let's say undefined. Well, you can try this point, 1, 0. What do you have? Undefined. Or we can say vertical asymptote because it goes up. Okay. That's why we say circle here. On the left and right end points, you will have infinite changing rate. Technically, can't do this. Sounds good. All right, so this is how we do implicit differentiation. Number one, you can do it with explicit if you want to do the algebra and solve it. In general, don't recommend. Okay. Second, just do the differentiation directly. If it's all x, period. If it's all y, take the derivative and then times y prime. Okay, that's the only thing we need to be careful of. By the way, do you realize this is what we have from implicit? This is what we have from the explicit. Do you realize they are the same thing? Because y equals square root of 1 minus x squared. Because it's on the circle. Okay, so you receive the same thing, no matter what. All right. That's it. Let's try some examples. Okay. Let's do it together, slowly at first. Let's do x cubed plus y cubed equals 6xy. We want to find y prime at 3, 3. If you want to solve for y, stop doing that because you're solving a cubic. We don't even know how to do it. Instead, derivative on both sides. X cubed, 3x squared. Y cubed, 3y squared. But for x is okay, for y, you times y prime by the chain rule. See the difference? Okay. On the right, what do you have? 6 is a constant, take it out. You have the derivative of x times y. Now you need to be careful. What do you mean by x times y? Well, if y is a constant, it's almost like x times a. We know the answer is a. If a is a constant. Right? Is y a constant? No. Y depends on x. So y is actually a function. So compared to this, you should handle this one more similarly to x times some function of x, because y is a function of x. Still okay? How do you do this? Product rule. Therefore, you better do product rule for this one. Don't treat your y as a constant. Okay. Well, x prime is just 1. Xy prime, just keep it that way. Sounds good? Your job is try to solve y prime. It's here and here. How do you solve it? Move all the y prime to the left, everything else to the right, factor things out, and divide. So that's exactly algebra. Of course, you can do 3 by 3 later. We have the answer. All right. Questions? Good. From here, you can see implicit differentiation is not hard because everything before follows. You have the power, sine, cosine, exponential, whatever, just apply the formula. Product rule, quotient rule, chain rule, just apply the formula. So everything will be okay, except for one thing, okay? That is every time you see a y, after you take the derivative, you times y prime. Everything with x, just as before. Sounds good? So imagine if I give you any implicit differentiation, you just start taking the derivative, what's gonna happen? Some term is straightforward. Any term with a y, when you finish taking the derivative, you will produce some y prime, right? So if you have several terms, some term after you differentiate it has no y prime, some terms has y prime, you move everybody who has y prime on one side, everybody has no y prime on the other side, you will always be able to solve it by doing the algebra. So this is always doable. Okay, before we try more examples, this thing here we just did has a fun name. It's called volume of Descartes. Okay. To see the shape, let me share my screen. The shape look like this. Okay, you can play with the number here. We pick a 6, but you can do 5, 4, 5, 6, 7, 8, or maybe you can do 10. Okay, maybe 100. Okay, no matter what you do, that basically changes the size of the volume. So that's something fun Descartes discovered. And back to this, remember what we said? We want to find the derivative at 3, 3. 3, 3 is here. Okay. The answer we found was -1. So if we put the thing here, -1 times x minus 3. Okay, you can see actually we find the tangent line with no mistake. So everything works perfectly. Okay. By the way, have you ever thought about how to play with this by deleting the y here. Okay, I'll change it to be y. Okay. Have you ever thought about take this one and change it to be 4th power? Okay, 5th power. Okay, and keep going. So you can play with this all the time. Let's do 50. Oh, okay, yeah. What do you think will happen to 500? Do you realize this one actually give you 2 square? What about 5,000? It's almost like a square. Okay, so there's a lot of things you can play with those kind of patterns. This is actually a source of a lot of, how to say, art design. Another thing I can show you, which I will show in detail next time, is something look like this. Okay, sine x, sine y, but you put a constant here. You can change it to be 2, 3, 4, 5. Make it symmetric. Okay. Now what you can do is you can take a equals 1. The graph look like this. Not so interesting. A equals 2, 3, 4, 5, 6. Okay, let's try 16. Okay, that's actually another source of designing of a lot of architectures and arts. So actually mathematical patterns is everywhere. The beauty is actually you can find the hidden knowledge in this thing, because if I just show this graph, there's no way you will know how people generate things like that other than this is just great. But actually, if you think about it, it's just a simple pattern once you can find it. The beauty in nature is we only see this. How are you supposed to guess what's behind it, which is just a one simple formula? How do you know that everything in the world is described by a simple formula, which is F equals ma? That's the beauty of science, okay? Some people call it computational irreducibility. That is, you see something very complicated, but if you just narrow everything down, you find that actually the pattern is pretty simple. You just repeat it for a lot of times. That's why you see something fancy. Okay, cool. That's all for today. Tomorrow, we'll do more examples.